Welcome. So I'm going to talk about ProxySQL deployment in Pinterest. This story covers provisioning of ProxySQL. At this point, I expect that everybody is convinced ProxySQL is an awesome product. You should use it. And I will show how we use it in Pinterest at scale. So what's the problem anyway? Why this talk exists and what do we do differently? What is specific about Pinterest? There are several problems. Problem number one is there are many ProxySQL instances. So we have our databases are sharded, obviously. And we have a concept of a backend type, right? Which is, you can think about it as a vertical shard, a functional shard. And for each backend type, we deploy a pool of ProxySQL servers. And we have a lot of those backend types, at least more than 100 last time I counted, and more than 400 EC2 instances. So there is a lot of instances, and we need to manage them with a relatively small team. Each backend type has different configuration. You know, some users want to use one features. Some users use cache, query cache. In some backend types, we use different routing schema. We use port-based routing. We use username-based routing. Sometimes we even used regex-based routing. So we need to be able to configure everything efficiently. The second challenge is we run it in cloud environment. Again, what is so special about it? In cloud, instances tend to come and go. They are less. They live less time comparing to bare metal, and we kind of treat them as cattle, as opposite to pets. And in fact, we even enforce shorter lifetime of each instance. I think 90 days or 30 days. And not only instances live short, but services also have their life cycle. For instance, some services are experimental. Developers start writing something, the project doesn't take off, so they shut down the service. And as an infrastructure team, we need to support that. We need to be able to clean resources in a graceful way and do not produce craft, because, you know, in a cloud environment, you pay not only for what you use, but also for what you forgot to destroy. So that's the second challenge. And the third challenge is if you ran many instances of anything, you know that configuration drift is a problem, right? So you need to make sure that config of instance is what you expect it to be. And usually people solve this problem by immutable infrastructure, especially in stateless services. For stateful services, this doesn't really work well because you don't want to rotate whole your fleet of databases or ProxySQL instances simply because you upgrade some tiny bit of config. And I like more a concept of disposable infrastructure, which means we can make changes, but at the same time, our infrastructure is built in a way that we can dispose any instance at any time, and that will not affect the service. And one more to add is we want to know who made a change, what was the change, and why it was made, right? So we want to keep audit trail, not only for compliance purposes, just even for us to understand why did we configure ProxySQL this way, okay? So these are challenges, and in this talk, I will explain how we solved that problem. So what will you take from this talk? I will talk a lot about Terraform. I'm a big fan of infrastructure as code, and Terraform is a big part of it. I will also talk about Python development a little bit, but still significant chunk of this presentation, and a little bit of Puppet. Okay, so we approach this problem with 3 stages of provisioning. If you think about ProxySQL as service, you need to run it somewhere, right? So we run on AWS, so before we can provision ProxySQL, we need some AWS resources to run it on. That part is covered by Terraform. We create resources, and then we pass these resources to next level of provisioning, which is Puppet. Puppet is responsible for, so when we start EC2 instance, Puppet is responsible for installing repos, packages, configs, and starting services. We do not rely on Puppet a lot, mostly because I don't know Ruby, but also it's not very flexible comparing to Python, and a lot of dynamic provisioning is done by Python software. So when Puppet works, it starts ProxySQL instance itself. It starts ProxySQL Manager, our Python software that manages ProxySQL. And the rest of the configuration is done by this Python software. We also let it modify the configuration. If we need to change it, we do not want to wait until Puppet runs, every 30 minutes or so. We delegate this function to Python software that can react quicker than that. Okay, so basically I will explain each of these parts. The principles. I'm a big believer in infrastructure as code, and this is the whole provisioning story is around infrastructure as code. For users, we provide Git as an interface. So if you want to change something, you create this change as a PR. In our case, it's a diff because we use Arcanist, but again, still diff. Git. In future, I think to make it friendlier, we may create web services, web interfaces, but underlying interface will be still Git, and that's on purpose because Git provides you audit trail. you know, when you create a PR, you can describe what it is, you can link it to a Jira ticket, and in Git log you have all history. So it's very good for compliance. It's good for, you know, general understanding what was going on and why. Next, we on each level of provisioning we try to use declarative interface. Terraform obviously supports declarative interface. So does Puppet. And in Python part of the provisioning, we still have declarative configs, because the ProxySQL configuration exists as a config. I will show JSON files so it will be more clear. I think declarative approach is it's not better, but than imperative approach when you execute commands on EC2 instances. It's kind of next level of abstraction, and behind any declarative piece of code, there are some imperative instructions. So in my opinion, it's when people compare what is better, imperative or declarative, it's not entirely correct in my opinion, because declarative is easier, less flexible, less room for a mistake, but behind it, there are imperative instructions, right? There is Python code, there is Ruby code, if we talk about Python, and there is Terraform provider, if we talk about Terraform. Now, so each of these three provisioning layers, they also have different frequency of changes, I would say. Terraform is the least frequent change. You create load balancer, you create autoscaling group, and you don't change it. Unless there is a good reason to do so. Puppet is more frequent change. If you need to upgrade management software version, this is the job for Puppet. If you need to update config, again, this is good for Puppet. And Python is very frequent change. If there is a new MySQL server, Python registers it in ProxySQL. If there is a failover, all additional features we implement in this ProxySQL infrastructure is done by Python. Okay. So, what we provision? This picture describes a piece of infrastructure that I will cover in this talk. We do have clients. We do have MySQL replica set. And proxy layer is this. We need to provision load balancer. We need to provision autoscaling group, and all supporting AWS resources to make it work. The ProxySQL pool is, it spans multiple availability zones. So if you create a load balancer in AWS, you specify in what subnets you want this load balancer to be deployed. And virtually, it looks for you like one entity, right? NLB. Underneath, you have a load balancer node, how AWS calls it. And there are as many load balancer nodes as subnets. The same story with autoscaling group. You can span it in one region across multiple availability zones, and you you can have EC2 instances in different availability zones. So data flow usually works like this. Network load balancer provides a user a DNS name, right? When you create NLB, Amazon gives you NLB DNS name, and it usually results in at least 2 IP addresses. On top of that, we create a CNAME, which is user-friendly for application, because it doesn't change even if you recreate load balancer. And the nice feature about this is that when you resolve the CNAME and the NLB DNS name, usually the client gets IP address in the same AZ as the client itself, right? So if you have 3 IP addresses on your NLB, and you have a client in US East 1A, usually the client gets IP address in the same AZ, which means the client will talk to this node, which means this NLB node, it will forward traffic to instances in the same AZ. We actually disabled cross AZ forwarding just to make sure that this data flow is local. Not only it's better for performance, but it's also, cheaper. Amazon doesn't charge you for this traffic, but it does for inter-AZ traffic. For that, we need to ensure that at least there is one instance in the same AZ. And then, of course, we need to forward traffic to a master. Master can be in different AZ, but what can you do? Okay, so we need to provision from here, NLB, auto-scaling group, and that's it. Terraform. This is how it looks for a user. If I want to create a ProxySQL pool, I write this piece of Terraform code. This is a module. I specify, let's say, unique input values for this particular ProxySQL pool, right? What is remarkable about this? Well, notable, not remarkable. I specify like backend type, what shard it is. I specify health check type. I will cover this part because it's important for ProxySQL. Usually, full provisioning takes about 10 minutes from until Puppet finishes, until ProxySQL Manager finishes its configuration. So about 30 minutes to make sure that everything runs and everything provisions. Minimum auto-scaling group size is at least number of subnets. This is important to have at least one ProxySQL instance in each availability zone where we run ProxySQL. Okay, and the CNAME. CNAME, that is DNS name that you give to a customer to connect to the database. Module. I like this concept in Terraform. It's not new. It's very similar to functions in normal programming language. And it gives you many benefits. I mean, using modules. So if you use Terraform, you should use modules. Some companies, even on the policy level, they do not allow to create individual resources. They want you to use modules. So we use modules. Why? Because if I create a ProxySQL pool, I can easily create the second ProxySQL pool, and it will be exactly the same. So the infrastructure you create is repeatable, right? If you want to decommission ProxySQL pool, that's as easy. You just remove the module and Terraform correctly destroy all resources associated with that ProxySQL pool. It's also friendly to your junior colleagues, right? If you have some DBAs who are not familiar with AWS or not familiar with ProxySQL, they can create ProxySQL pools with this module, and it will be no different from what I create. So it kind of splits complexity between different people inside the team. We have module maintainers. I maintain this ProxySQL module. My teammates use this module. If they want to dig deeper, they can, right? They can update the module, but they don't have to. They can be just users of the module. The module has a version. Again, this is very important to keep track of your infrastructure, keep track of complexity of the infrastructure, and if you introduce some new features in the module, you can be sure that you are not going to break existing stuff, right? So that's good. And one more benefit of the modules is that you can test them. In this talk, I will show you how we test Terraform module, and I will use zero downtime migrations as an example. So what's inside the module? I create a bunch of AWS resources that I need to deploy ProxySQL. I group them in several files, and they serve slightly different purposes. Autoscaling is a file for all stuff associated with autoscaling group. I create launch configuration here. I create autoscaling group itself. I define autoscaling policy. Cool feature in AWS is it can add more instances to the autoscaling group if average CPU is higher than a threshold. So you can scale up and down depending on your load. Load balancer, you create the load balancer itself, you create listeners, you create target groups. And finally, DNS. When you get a DNS name from NLB, you can create a CNAME that you can share with the client, and the client uses that CNAME to connect to the database. Plus outputs, I cannot tell that we use them much, but for migrations, it's nice to have the DNS name, and we export it as the return value of this Terraform module. Okay. Now, health checks. This is important for ProxySQL because traditionally load balancers were created for HTTP servers, right? And in ProxySQL is not HTTP server. It's different. It's more stateful versus HTTP, and we need to understand how to. We need to be able to work with it. So in AWS, there are two decisions to make, right? AWS needs health check to make two major decisions. One is, should I forward traffic to this target? If the target is healthy, the load balancer will use this target. And by target, I mean the EC2 instance. AWS calls it a target group, so EC2 instances are targets. Don't get confused. The second decision is, should I replace the target? Should I terminate the instance because it's not healthy? So these are two decisions, and it's important to keep that in mind. And there are two health check types that you can define on the auto-scaling group level because they behave differently. One type is ELB health check. Basically, this is a health check that is responsible for both the decisions. How it works? First of all, for network load imbalancers, the health check, the health probe, is not HTTP request. Okay? To check the health of the instance, NLB establishes a TCP connection. And if the TCP connection is successful, then health check is successful. It's different from application level balancers, ALB, application load balancer, when the load balancer makes HTTP call and expects 200 in the return. Okay, so NLB establishes TCP connection. If the connection is successful, the target is good. If it's not, if the connection is not successful, not only traffic is not forwarded to this target, but also this target is decommissioned. It's terminated. Originally, I wanted to use this type of check because it seems more convenient. So what I wanted to do is, ProxySQL listens to a TCP port. I think it's 3306, 6033 by default, but I'm never gonna remember that number, so I changed it to 3306, right? But I wanted to, in ProxySQL Manager, to implement this logic. If I believe that my ProxySQL instance is healthy, I'm gonna listen to 8080. If I think that my instance is not healthy, I stop the server, it doesn't respond to health checks, and Amazon will replace this instance. Okay? So that was the original intent. Unfortunately, it didn't work well for us because suddenly instances started to disappear. And I couldn't understand what's going on until I ran TCP dump, and I found that Amazon sends many more health checks than I expected. I configured to send one health check every 30 seconds. Instead, what I saw was one health check per second, and sometimes even more often than that. My TCP server was primitive, single-threaded, so sometimes it couldn't keep up with health check requests from AWS, and the instance was considered unhealthy, and a few times we had like all our ProxySQL instances are gone. Horrible situation. So instead, I changed to EC2 type health checks. They're less aggressive. So the target group still wants a TCP port to make a decision whether I should forward traffic or not. So I ditched this idea with a dedicated health check TCP server, and instead I I specified 3306 as a health check port. So when ProxySQL is performant TCP server, so I'm not worried about frequency of health checks, and it works reliably. And obviously, if ProxySQL isn't running, it will not be listening to 3306. So I will still be able to replace the instance and stop using it. On top of that, so another decision, whether we should terminate EC2 instance or not. We have some additional logic around it, right? And ProxySQL Manager explicitly marks instance unhealthy if it thinks that it is unhealthy, right? But Amazon still helps you to take unhealthy instances out of rotation when, let's say, if instance runs on degraded hardware, Amazon issues EC2 event, right? And this is a signal for autoscaling group to decommission this instance. So if instance, goes down because, Amazon terminates it, it will be gracefully removed from autoscaling group, and EC2 checks still support that. So we're good. I run now ProxySQL with EC2 type health checks, and it works well. So basically, in the Python code, we have several checks, and they check different things in ProxySQL instance. If everything is fine, it marks the instance as healthy, and if it gets exception on any of these, it marks instance unhealthy, and then instance gets replaced. Okay, the point of this, use EC2 type checks. Gives you much more control over instance replacement. Now, zero downtime migrations. So we have load balancer, and we have autoscaling group. What happens if we need to change AMI? Normally, you would change launch configuration. And you would need to make sure that all the instances are removed, and all new instances will pick up the new launch configuration, and effectively, you will run on a new AMI. Plus, in several cases, you need to change autoscaling group as well when you change subnet or security groups. So these are relatively destructive changes, but you still have to do it, and you still have to make sure that there is no service disruption, ProxySQL up and running. So we developed in the Terraform module way to do kind of green-blue migrations to ensure zero downtime. It works. The idea is very simple. You create new autoscaling group. When the new autoscaling group is ready to serve traffic, the old autoscaling group gets destroyed. So this is all taken care by Terraform, which is good. It's good for a user. You don't have to do it manually. You don't have to watch, half an hour until everything is provisioned. So it's very convenient. But you need to make sure that it's really zero downtime, because it's a good idea not to trust anything and verify. So I will show you how we do that. So first of all, we need to configure these zero downtime migrations in Terraform. If you just update launch configuration, it doesn't impact autoscaling group. It will not change the autoscaling group. Eventually, yes, instances will be replaced, but you don't have control over that. By the way, I developed this before Amazon launched a nice feature which is called instance refresh in autoscaling group. This is a nice feature. Sometimes we use it for bigger migrations, and in theory, it could probably replace this approach as well. So the idea is you can trigger instance refresh, and AWS will start taking out EC2 instances from the autoscaling group, and so it takes out one, then replaces it with a new instance, make sure that it's healthy, and then replaces the next one. And that happens without user intervention. So you can just launch instance refresh, and eventually it will be done. Maybe next day, but without your supervision. Okay, with Terraform, we do it a little bit different. So first of all, we need to establish artificial dependency between two resources, launch configuration and autoscaling group. I do it by including launch configuration name into autoscaling group name. So when you update launch configuration, Terraform has to update autoscaling group as well. Okay, so that's step number one, dependency, inject dependency. Second is, I would say, correctly link target group and autoscaling group. Terraform provides two ways, and I found experimentally that one way doesn't work with zero downtime migration, and if you want it to work, you have to do it like this. So one way is you can create attachment. So attachment resource. It's a virtual resource that that way Terraform knows that you need to attach this autoscaling group to this target group. Okay, so it doesn't work with zero downtime migrations because Terraform needs to delete that attachment. When you delete that attachment, target group stops serving traffic. So it doesn't work. But this way, it works. I don't know what happens behind the scene, but fortunately it works. Experimentally proven. And the last bit is to tell Terraform that if it needs to modify autoscaling group, first it creates a new one, and when new one is ready, it should destroy it. Only after that it should destroy the old one. Okay, so this is the Terraform part of it. Now, how to test this? How to ensure that it really works? It's really not impacting the user traffic. So the idea is following. We create ProxySQL pool. Then we start using it. While we use it, we create a replacement. And after everything is done, after migration is done, we check the log of this external monitor and see if there were any errors. On the EC2 instance, for the test, I do not run ProxySQL. Instead, I run a web server. It doesn't really matter whether it's a ProxySQL or HTTPD. What is important to have something on the instance that would respond to requests. So I run HTTP server because it's simpler. And this is how it looks like in the Python code. This is PyTest. I don't know if you're familiar with it. It allows, it's a framework to run Python tests, but you can use it for anything, basically. I use it for Terraform. So idea of unit test in Terraform is different from Python. In Python, what you do, you take a function, you execute that function, and you check the result, right? If in your function you have external calls like database calls or web HTTP calls, you mock it out and you fake responses, but you make sure that your function correctly processes those responses, and that constitutes the unit test, right? With Terraform, the idea is a little different. If you want to test something, you need to use the module, you need to create the resource, then you need to validate it, and then you need to destroy it. So it's not unit test in a sense of traditional software development. So when I test a module, I actually use that module. I create this module on real AWS infrastructure, I do my validation, and then I destroy it. For that, I developed a little library, terraform-ci, that provides you with some functions like terraform apply. It can be used in a with construction, which is convenient way to create and destroy resources. Even if you get exceptions somewhere along the way, I can be sure that created resources will be destroyed in a clean way. So this is what we do in a test. First, I create some user data in a ProxySQL instance that creates a web server. Then I apply this configuration. I run terraform apply. Then I start a Python child process that runs ping. In fact, it's a loop with HTTP requests, so it's not ICMP ping. Then I change the user data in my ProxySQL module. That enforces the module to recreate autoscaling group. So I apply it, then I terminate the child, and I check how many errors I got. This is the idea. So in this directory, terraform dir, I actually use my module. So this is how it looks like. I create some basic, simple ProxySQL pool on a smaller instance. I specify user data, and the user data actually installs a web server and serves this file, index.html. Very simple. And then I run it and just make sure that this validation code is correct. You can add any validation logic here, but in many cases, for me, it's enough that terraform apply doesn't fail. Okay, now Puppet. So if you think, question.
What's the benefit of that over, like, say, Atlantis apply?
Well, Atlantis you use for live repos, right? And here we are talking about a test.
Right. So Atlantis applies the test environment, and then we just change the thing instead of tell it we're going to prod. That's the same thing.
How do you destroy it? How do you destroy resources?
Same thing in Terraform. You tell it it's behind the Atlantis apply will
I've seen Atlantis a couple years ago. I don't know how it changed. It was my impression that Atlantis is good for CI/CD, right? When you create a PR, Atlantis will generate a plan for you. It will publish on nice web page. You can review it, you can approve it, and then you can apply it from the same web page, and Atlantis will do it for you. So it's great for for Terraform live repos. How it works with testing, I have no even idea. I don't know.
Yeah, we just direct to the QA environment instead of, yeah, that's just a different area we have in our.
Different environment, okay, but it's still live repo. Again, how do you run validation logic? You know, it's convenient here that you have everything in one Python test, in one Python code. You create resources, you run some validation logic, and then you destroy resources. When, let's say, some of your tests fail, you want to destroy everything, because if you keep environment live, if it runs for a significant amount of time, it will change over time. Its state will be unpredictable, and tests will be unpredictable. Here, you start from zero, and you want to end up in the same state, right? So you create resource, you verify it, and then you destroy resource. So a little bit different idea. Okay, back to provisioning instances. So when autoscaling group starts EC2 instance, you need to provision it. And traditionally, what happens is there is a cloud init piece of software, which is written in Python, I think. Yeah, cloud init. So you can give cloud init instructions, and it will tell you what to do with this instance. In this example, cloud init can install packages, can land some files, can execute some commands. For us, I mean Pinterest, cloud init has limited functionality, again, intentionally, and all it does, it runs Puppet client. And the rest is provisioned by Puppet client. So in user data, we do not specify any logic, any running commands, etc. We just specify like what Puppet class it should run, and some attributes like SPIFFE ID of this instance or backend type. So it becomes from these attributes, team, environment, and role, Puppet constructs a manifest that it has to execute on this particular instance. Okay, so here we get ProxySQL profile. And the ProxySQL profile, it does quite minimal stuff. It executes Pinterest base profile that installs Pinterest repos, Pinterest services, configures operating system, that stuff, plus ProxySQL. ProxySQL profile installs ProxySQL package. It installs ProxySQL Manager package, installs config, and starts services. That's it. For ProxySQL, I don't know. Yeah. For ProxySQL, you know, ProxySQL can be configured with a file, right? And the rest of configuration is SQL interface. So we create a kind of Bootstrap file for ProxySQL that only includes username and password for admin. So when ProxySQL starts, we can connect to this ProxySQL and finish the configuration. So ProxySQL CNF is really, really small. It's literally, this is it. And the rest is configured by ProxySQL Manager. What I didn't mention in the Terraform part is that Terraform also creates a EFS volume, so we can store logs on this EFS volume. You know, when instance goes away, so do log files. And you need log files for postmortems to understand what was going on. So instead of relying on services to export files, instead I create the AFS module. In Puppet I mount it, and I use it for logging. So this is a piece of Puppet code that mounts this volume. The good news about this EFS thing, underneath it's NFS server that you can use as normal NFS volume. And you can mount it as an NFS type file system. Okay, and I mount it, and I create a symlink. So this file is actually stored on the NFS volume or EFS volume. Python part. So how we are on time? 5 minutes. So we are over time? Okay, then I will skim this part. This is how workflow looks like. User has interface as Git to Fabricator or GitHub. Jenkins executes PyTest, and Jenkins also, when there is a new commit in the master, it deploys the configuration change to the source of truth, and the source of truth, the ProxySQL Manager agents, they watch for changes in the source of truth and apply the changes. Data model, I define ProxySQL configuration as a hierarchy of classes, right? And those classes implement properties and implement methods that I use to work with this configuration. For example, the init function in a class implements ProxySQL constraints. You know, ProxySQL enforces you to have some specific values of these attributes, and to make sure that the configuration is valid, we implement this in the init function. PS list, it's a list of configuration options, which is equivalent of a table in ProxySQL. And source of truth is a set of classes that defines ProxySQL configuration, source of truth configuration. It can compare these two. If there are changes, it applies the change. Okay. And ProxySQL Manager, just piece of our software that we use for provisioning ProxySQL and for working with it. For example, to connect to admin CLI, we use ProxySQL Manager to do that, to find correct port, to find credentials, and to execute MySQL client. Time is up. Okay, thank you. If you have any questions, I will publish this deck, and feel free to catch me if you have any questions. Thanks.